Okay, so number 2 states the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function W, where WT is measured in degrees Fahrenheit and T is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of WT at selected times t for the first 20 minutes are given in the table above. So you're given in this table, you're given a function, which is a twice differentiable function. I think of this as the second derivative function, but they're labeling this function W of t. So WT is twice differentiable. So WT means to me the second derivative. Because if you can take the first derivative, you can get the second derivative. That's the derivative. That's the first derivative. You take the derivative of the first derivative, you get the second derivative. So twice differentiable just means that the derivative has been taken twice. And I put an example right here. Example would be if f of x is equal to x to the fourth, then the first derivative is 4x cubed. The second derivative is 12x squared. And it means that the function f is differentiable at all points in its domain, and the derivative f prime, regarded as a function, is also differentiable at all points in the domain of f. That's what that means. So hopefully you don't have too much trouble with understanding what twice differentiable is, okay? Okay, A says use the data in the table to estimate W prime of 12. Show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in the context of this problem. So we're talking about temperature of water in the tub for this problem. So what we need to do is estimate the derivative at 12. So the only way I can estimate the derivative at 12 without a function is to use the slope. So I need to figure out what numbers 12, well, I have to figure out 12 is between what two numbers. And if I'm looking at the table, 12 is between 9 and 15. So I have to use what you use in algebra. If you have 2 points, you're going to find the average rate of change. So we have to estimate the derivative at 12 with the average rate of change. So I would say W prime of 12 is equal to, it'll be W of 15 minus W of 9 over 15 minus 9. That's the same thing as saying M is equal to Y sub 2 minus Y sub 1 over X sub 2 minus X sub 1. Okay, same thing. All right, so my 2 points would be 9 and 61.8 and 15 and 67.9. So that's the same thing as saying W at 15, which is the Y value at 15 minus the Y value at 9 over the difference in the X values. So W at 15 is 67.9 minus W at 9 is 61.8 over 15 minus 9. And then I would I would calculate what that value is. Okay. Okay, so the value of W prime at 12 is 1.017 Fahrenheit per minute. So you need to make sure you have units there. And it says, using correct units, interpret the meaning of your answer in the context of this problem. So we're talking about the temperature of water in a tub at a certain time. So the interpretation would be the temperature of water is increasing. It's increasing because the derivative is positive at a rate of 1.017 degrees Fahrenheit per minute at time equals 12 minutes. Okay, so that's the interpretation that you need to make sure you have. All right. Okay, B states, use the data in the table to evaluate the integral from 0 to 20 of W prime of t dt. Using correct units, interpret the meaning of integral 0 to 20 W prime t dt in the context of this problem. So when you integrate a derivative, then you're going to get the original function in a sense. So in this context, it's a little different in the context of this problem, but the interpretation means the same thing. So I'm integrating W prime of t, I should get W of t. All right, when I take the derivative of W of t, I should get W prime of t. So what's important to remember is if I have W of t as a function, then the derivative would be W prime of t. And if I get if I have W prime of t, then the integral would be W of t. So this would be differentiating W of t, and this would be integrating W of t. So integrating W prime of t, and differentiating W of t. Okay, so going backwards. So the integral of W prime of t would be W of t, or I could say of 20. Well, let me do it this way. It would be W of t evaluated from 0 to 20. So I get W of 20 minus W of 0. So I have this on the table because my function is W of t, which is a twice differentiable function. So W20 would be 71.0 minus W of 0 would be 55. And that gives me just 16. All right. So, and when I integrate, I should get just the degrees Fahrenheit. Okay. Over in the interval, sorry. So it says, using correct units, interpret the meaning of 0 to 20, W prime of t dt in the context of this problem. All right, so this means we're talking about the temperature of water. So this means that the water has warmed by 16 degrees Fahrenheit over the time interval, over the interval from 0 to 20 minutes. That's what it means. It means that the water has warmed by 16 degrees Fahrenheit over the interval from 0 to 20 minutes. Okay? Okay, part C says for 0 to 20 minutes, the average temperature of the water in the tub is 1 over 20, integral 0 to 20, W of t dt. It says use a left Riemann sum with the four sub-intervals indicated by the data in the table to approximate 1 over 20, integral 0 to 20, W of t dt. Does this approximation overestimates or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. All right, so when I see average temperature of the water, when I see this 1 over 20, integral 0 to 20 WT dt, I'm thinking about average value because the average value format is 1 over b minus a, integral from a to b, f of t dt. Okay, so that should indicate that that's an average value format. All right, then it says approximate with using a left Riemann sum. So you want to approximate this right here. So you want to approximate the integral of 0 to 20 WT dt. So when I approximate, I'm using a left Riemann sum. So my intervals are from 0 to 4, 4 to 9, 9 to 15, 15 to 20. That's 4 subintervals. Using a left endpoint, my left endpoint of those intervals would be 0, 4, 9, and 15. All right, so I take 0, 4, 9, and 15, get the heights at 0, 4, 9, and 15, which is 55, 57.1, 61.8, and 67.9. So I want to take the width of each interval. Remember, these widths are not equal. From 0 to 4, there's 4. 4 is the width. From 4 to 9, 5 is the width. From 9 to 15, 6 is the width. And then 15 to 20, 5 is the width. So I have each height multiplied by the width. So the length times the width of the first rectangle, the length times the width of the second, and so on. So my result is 1,215.8. And then I have to take that result and multiply by 1 over 20, which I'm dividing it by 20, and I get 60.79. So this approximation, if you look back at the graph, it is an underestimate because all your area is not accounted for under the curve. So the approximation is an underestimate because a left Riemann sum is used and the function is increasing. So if the function is increasing and you use a left Riemann sum, that is going to be an underestimate. Okay? And that's pretty much it for this problem.